Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at a project on Mushroom Classifier and whatever we have learned so far from the beginner series as well as all the linear models in this intermediate series. We'll will need some of the skills from all those past topics that we have covered. And in this video, we'll look at how to write a machine learning model that can classify mushroom if that mushroom is an edible mushroom or if it is a poisonous mushroom. And for that, the data source that we'll use is from this source, which is the UCI machine learning repository. So I'll put the links for this data source in the description so that you can go ahead and download it. And what a mushroom is, you probably already know this. It's a type of fungus that belongs to the family of yeast or mold. And this type of mushroom, there are edible types which can be used as food. So you can eat mushrooms, uh, and there are other types which are poisonous, which you definitely don't want to touch. So how do we differentiate between a poisonous mushroom and an edible mushroom? So in this data set, there are different features. You remember the iris data set that's in Scikit-learn library. This is a similar one, except that all the features here are categorical. And so, for example, one feature is cap. And if you look at the description within cap, it could be a bell shaped, it could be conical shaped, convex, flat, knobbed, or sunken shape. So different types of cap shapes. And then second is stalk. So again, for the stalk, there are different shapes, different roots, different types of surfaces. So each of them have different sub features associated with that particular feature, and so on. Then there is a veil, which is, if I understand correctly, that's the membrane on the stalk of a mushroom. And there are gills. So if you see some of the mushrooms, they have these serrated fin like gills underneath the cap, and those are the gills. So using all these features, can we create a machine learning model that can help us classify these two types of mushrooms? So we are going to work on that. And before we jump into that, I just wanted to show you what the data looks like when you download this file. Uh, so the data looks like these alphabets, and each of these alphabets, so for example, the first column is for class. So the class can be either edible for E or poisonous for P. And so that's why it will have only E or P values in there. And then the second one, for example, this is X. So if you go, so that would be the cap shape, and the cap shape X represents that it's a convex shape, and so on for the rest of the file. So what I've done is, ideally, when you start working with data like this, your first job is to bring the data into Jupyter Notebook or any Python IDE that you're using. And so to read these files, we'll read this file as is. And then for this particular part, if this is because this was just one time, what I've done is uh, I've copy pasted this directly into the notebook and did some manual editing. But if you need, we could also write, one could also write a code to pull this automatically. So if these numbers were more than, if instead of 22, if these were 200,000 rows right here, then there's no way you could manually write that. So in that case, I would write a code. But because these are just 22, and the time it takes me to just manually edit this is far less than writing code for that, which I would use just one time. I prefer just doing the manual work for this. So let's go into Jupyter Notebook. Again, I've put the citation here for the data that we have. And then this is again from the UCI machine learning repository. Now for libraries, these are the libraries that I've imported. If the pandas, numpy, and this is a new Seaborn library. We'll use that for some plotting. And these are other familiar libraries that we have discussed so far in this series. The pd._set option, I've set the maximum number of rows and columns that we can display to 500, just because uh, by default it would show maybe just 10 or first 5 or last 5 rows. But if you really want to look through the entire data frame, then you could run this cell, otherwise it could be commented out. Now for data, I've already downloaded all the files into this folder Mushroom, and so I'll be reading the files from this particular path. In your case, you may have to change this to path that you have the folder located. And for data, uh, these are the classes. So we have E as the edible class, and then we have, for poisonous, we have P, and the proportion of both the classes is somewhat equal, 51-48%. So we need not worry about a skew in the number of records for either of those two classes. So we are good there. Then for the feature descriptions, this is the directory that dictionary that I've created. What I'll do, I'll post this particular notebook on GitHub so you can download it. So you don't have to worry about copying this text. You can just typing this text, you can just copy it from the notebook as is. And when you run this, we have 22 features. And what I'm doing in this particular for loop is reading all the items from the dictionary, and then this is one string. So what I'm doing is splitting the string by using a separator comma, and that's what I'm doing here with the split. And what that does is it splits these into multiple items within the same list. So that's kind of the easy way to fix that problem of uh, separating those values within there and putting them in quotes. Now for the data, this is what I'm using, pd.read_csv, and here we can specify the path that is mentioned above plus the name of the file. And because the file didn't have any headers, I've put the header is equal to none. And the reason you can give this particular input file any name. I've put this as df main because that's, I see that as a raw data frame, and any further modifications that I'll be doing, I'll save that in another name. So you don't have to reread the CSV file over and over again if you accidentally make any changes to the data frame that you want to revert, and if you want to revert back. So we'll run that. So path, I'll go ahead and run all these cells. So that is how the data frame looks like right now. The column names are 0, 1, 2, 3, 4 up to 22 because there's no header in that particular data file. So one of the first steps that we need to do is fix that. And to do that, we need to add column names. So let's do that. Add column names and df main dot columns. So if you remember, if you type this, what you get is the name existing column names. So what you want to do is change that. So what I'll do is put a is equal to sign and then put the list of keys. So these are the common column names from the dictionary that we need. So these are 22. So let's add that list, and attr. So those are the attributes and keys. So keys, if you anytime if you type dot keys and open close parentheses, you get the all the keys for the dictionary, and that's what we are doing here. And what I'm doing with the list is just putting a list there, so we get them in a list form. Now once we have that, this is not going to be enough, because what those dictionary keys are just 1 through 22. The first column, which is at 0, that is not in that dictionary, so we'll have to add that manually. And to do that, I'll just add the name string class, and that will go in front of that. Now if we run this particular cell and look at dfmain.head, we can see that the column names are now fixed, so we have proper column names to each of those columns. The next step that we can check is, are there any missing values in the data set that we have? So check for missing values. Now the steps that I'm walking through, they need not be exact same order. Everybody has a different style of how to proceed. In this case, this is just how I would proceed working with this data. Df main dot is na. So when you type is na, you get you'll get an true or false if that particular cell is or uh, is not null. And so if you sum over that, then you get, if there are any na values, then you'll get a number here. So in this case, everything looks good, all are zeros, so it means that there are no missing values in this particular data frame. So once we have that, the next item that we'll can do is, because we need to do pre-processing only on the train data and not the uh, only on the features, and not on the target, not on the output, just the input, we'll separate that out here. And to do that, what I'll do is split it. So let's do this would be split training features and output class. So we'll separate those and put them in x and y. So x main is equal to df main dot columns, and there are different ways to do this. Again, this is the way I did for this particular video. So you could type df main tilde df main dot columns dot is in, and here you can specify class. So what this particular part is doing is, we are looking for all the columns in the df main data frame which are not equal to a class, so all columns except class. And so those are the columns that we will get in here, and then we'll put those and those are the only columns we'll get from df main. So so if we now look at x main dot head, we shouldn't see the column 0, so the class column is no longer there. We just have 22 columns instead of 23. And for y, it's straightforward. We just need that column of class from the df main data frame, so we have that there. And we can always look at what columns we have without pulling the entire data frame by just typing x main dot columns, and here we have the entire list of columns in the data frame. Now in this case, we already were given the proportion of the two classes in the data set. However, it's in most of the cases you may not see that, so it's a good idea to check the proportion of each class in the data frame or in the data set that you have. So here let's go ahead and do that. I'll use the df main because we have that associated class still in that column of class. So group by, and we'll group by our class and then just count class, and there we go. So here, as you can see, for edible mushrooms we have around 4,208, and for poisonous mushrooms we have 3,916 samples or rows, and they are almost 50-50, so we are good there. Now let's begin with pre-processing. You could also say that some of the steps that we did earlier could also come under pre-processing. There's no standard delineation of what step could be considered as pre-processing. So here, what we'll first do is create dummy variables. Now, for creating dummy variables, I know we have covered the one hot encoder in Scikit-learn, so that's definitely the route we could take. But in this case, it was just easier to use the Python so pandas get dummies functionality. So I've used that. Xmain is equal to pd.get underscore dummies, and here typing xmain, and we don't have to worry about the output target y because we've already separated that out earlier. Now if you look at the number of columns, we have 117 columns, and the reason is because the in what that function did is pulled each of these uh, features, sub features within each of these features, and put them in a separate column and flagged it as 0 or 1 based on if it was in that particular sample. So if we now look at xmain dot head, we can see that uh, the zeros indicate that that particular feature was absent for that, and if you see a 1, it means that that particular feature was present for that particular sample. For example, the sample at index row index 0. Now once we have this, we are good to move further because these are all numeric. There is no non-numeric data in the data frame now. The second item that we need to check is collinearity, and so let's do that. Check for collinearity, and the reason why we want to do that is if there are features within these data frame that are correlated to each other, we want to remove those, and we need a data frame where each feature is each feature is independent, so we don't want uh, two features that do the same thing. And for that, what we'll do is we'll calculate the correlation coefficient. We'll calculate the r square value and put that in the variable x underscore corr. And to do that for the entire data frame in one step, there is a simple command called corr and open close parenthesis. What this gives is a value of r. So to get the r squared value, you need to square that. So once we run this, we have the cox, this particular output, where we can see that the diagonal terms are all 1, and the off diagonal elements is the correlation between this particular feature and this feature, and this feature, which has correlation r square value of 0.037350. So that's for all the features. Now here it's difficult to visualize and go through this particular set what I was talking about earlier, let me go a step back. You see that these are dotted lines. We cannot see the entire data frame. So to fix that, what we want to do is run this. So we'll see up to 500 rows, maybe not all, but this has only 117. So we should see the entire output. Okay. So as you can see, the diagonal elements would be all all ones, because that's the correlation of the feature with itself. And so that's how that goes like this. And then off diagonal elements are the correlation between this feature and then the rest of the features in the dataset. To make this easier, what we can do is we can plot this as a heat map. Let's do that now. And before doing that, let me add a note that says that all the labels may not be visible. And by that, what I mean is because we have how much 117 labels, and there's not enough space for the x and y put that, so we may be missing some labels in there. plt.figure, and here we can specify the fig size. So to start with, let's just put 10 by 10, and then later on I'll change the size. sns.heat map x underscore corr dot round, and so here you could put annotation is equal to true. For example, an ot is equal to true. We can comment that out later on if we think that we cannot read anything in there. So once the plot is ready, we should be able to easily identify features that are correlated. And later after this, then I'll show how to get rid of those uh, correlated features. So if there are two features, we just keep one and then remove the other one. And this might take a while. Okay, so we are back, and this is the heat map that was created. And as you can see, if I zoom into this, we cannot read any of the annotations within that particular plot. So I'm going to go ahead and comment that out. And again, for the number of the labels here, we cannot see all of them. So what I'm going to do is increase this figure size to 2020 and rerun this. So yes, so now we can see, so this is the entire plot, and we have the features on 117 features on y, and I'm guessing 117 or maybe less on the x-axis. All of them may not be visible. So the diagonal line, that's the value of that's the value of 1, and as you can see right here, which is 1, and the darker the value of the square, the closer that value is to 0. That is to say, no correlation. So we need the darker the pixels, we are good. Light pixels, we are not good. And so here there is this feature which is the whale type p, and that seems to have just 1 as a value for the entire column. So we need to get rid of that. And then there are these features such as this one, which is stock color below rings underscore c, and that is this feature, and that seems to correlate with order m. So what we need to do is keep just one of those two features. And so the reason for removing the collinear features is to get a better prediction accuracy in the model that we create. Now to do that, what we'll do is we'll write a function that checks the value of r square, and if that value is greater than or less than, let's say, greater than 0.7 or less than minus 0.7, then we flag it for removal. So let's create that function now. So remove correlated columns or features, and for this, and we'll label this as remove underscore collinear underscore columns, and this takes in value of x. Now the first item we need to columns is equal to list x dot column, so we get the original list of column names, and then we can go ahead and print number of features before, and this is going to be length of the columns variable that we created above. Then we'll create two for loops and we'll iterate through that particular data frame x underscore cor, or for call in columns, and for I call in columns. What we need to do is if column, so if the outer column is not the same as what's inside this, so that is to say if we are not checking the correlation between the same column, so that's what we are doing here. If those are not the same, then we get the r square value, the np dot corr coef and x column, so and then x I column, so that's two columns, and we get the r, the correlation coefficient, and so it will be a matrix. So what we want to do there is get just one of those values. Right, because this is a square matrix, we get the value from row 1 and column 2. So just to illustrate that point, let's try this habitat underscore p and habitat underscore w. So let's try that. Habitat underscore p and habitat underscore w. So if you run this and get the correlation, x is not defined. So let's go back up. We still have that as x main. So let's type in x main there. So this is what we get as an output. One is the correlation of habitat p with habitat p, and this is the correlation of habitat p with habitat w. So this is value of r, and we need just this value. So what we do is just say 0 1, and so we just have that value. Then we need to square that, so that's the squared value, and that's exactly what we're trying to do in this line. And once we calculate that value, we need to check if that value is greater than 0.7. So r square value, if it is greater than or equal to 0.7, or so put a pipe there, that value is less than or equal to minus 0.7. So we have that, and then if that is the case, then what we want to do is remove that particular column from the columns list that we have above. And so this way we are removing one of the columns that is correlated with one other column in that data frame. And after that we can print number of features. This is after we remove the collinearity, and this is length columns. So this should be lesser than what we started with, and before we exit we need to return columns. And so that's the function. Now to get the updated list of columns, let's create another variable, only non-collinear features, And for this new underscore columns is equal to remove underscore collinear underscore columns x main. So that should give us, this was before, and let's see what we get after the collinear features are removed. So we have around 100 features. So what we can do now is, just for sake of experimentation, we can have an option here. So if we want to use the with collinearity, we can set the value of x is equal to xmain.copy. So the function never used there, but I'll comment that out now. And where we remove the collinearity, removed collinearity. So here I'm putting the value of x is equal to x main and columns. So this x will now have only 100. So let me, it's called new columns, and so on that. So we just have 100 columns in there instead of 117. Now, if we look at again the same heat map that we had earlier, we should be able to see everything dark color. And before we do that, what we need to also do is remove this particular line. This is whale type P. So let's write code for that. Remove columns with zero variability, because those features don't explain anything that could help the model. So we are going to remove those. And in this case, again, the method is the same. We first check if x dot columns dot is in, and here we'll type whale dash type underscore p, and this we will negate this, so we don't want that column. And so what we can then type is x dot columns, and then from this we need the value for x. And so here if we type x dot shape, we should see 99, and so that's what we see here. So we removed that column from the data set. Now if we plot again, so plot after we removed all the collinear features and the features with zero variability. Now let's try calculate the correlation coefficient again, and this time we'll use x because that's the one that does not have those correlated features, and we square this, and then let me go ahead and copy so we don't have to type everything. Copy, paste that here, and rest stays the same. So now if we run this, we should be able to see a nice clean heat map with little to no bright spots in there, and that's exactly what we have. So if you look at this plot, you see these spots, we removed all of those here, and this is nice and clean. So now with this, I think we are in a good position to move forward towards the modeling side. So let's split the data now into train and test sets. So do that. This could still under be processing, so preprocessing data. And remember, because we have all the features that are just zeros and ones, there's no need to do a standard scaling in this case. So np.array will convert the data frame to an array, and then use that for our x train, y train. So x underscore train, x underscore test, y underscore train, y underscore test is equal to train underscore test underscore split x comma y, and we can print the shapes. So print x underscore train dot shape x underscore test dot shape, then y underscore train dot shape, and then your y underscore test dot shape. So with that, we should be able to see a nice split. Okay, so just to check again, 093 plus 2031, we should get the original number that we started with, and that's what we have. So if you look at df main dot shape, that's the total number of records, so we are good there. Now let's create the write the code for model, and because we are going to run several models, what I'm going to do now is write a function that does the fit and predict. So instead of writing the code for that over and over again, we'll just call this function so that it'll automatically do the fit, predict, and then calculate the matrix for us. So let's call that function fit underscore predict, and it'll take the classifier as an input. And I'm just going to add some print lines here to look to so that it makes the output easier to read, and print the model. Sorry, the classifier that we'll be using. Then first for train is exactly the same method that we have been using so far. clf.feed x underscore train, y underscore train, and then for predict, we just use the clf again. So y underscore pred is equal to clf.predict, and this is based on the test set now. And finally we have the matrix, so accuracy, and for accuracy we use the matrix dot accuracy underscore score, and we use the x test and then y pred for that, and we can print that. So accuracy, and that is equal to ACU, and then we have confusion matrix. So we'll use the standard scikit-learn without doing any fancy heat map output. CM is equal to matrix dot confusion underscore matrix y underscore test y underscore pred, and then just print that out. Confusion matrix, print it on a new line, CM, and after this we'll just return the accuracy score and maybe the confusion matrix as well. So that's the function we have. And for the type of models that we want to run, we'll put all of them in one chunk in a for loop. So the loop will iterate through it and do all the fit and predict and everything automatically. So we'll create a list that stores all the outputs, and then from clf name in, so here is what will create that list. So let me go back a step. Okay, so here the very first one, put that right there, and put this one here, and the first one is linear underscore model dot logistic regression. So we have done this, and let's set the penalty to L2 and tolerance to 1e to the power minus 2, and solver is equal to lib linear, and then let's give this name logistic regression classifier. So that's one. And then the next one, now if you're asking why did I set this to L2, why is the tolerance this, so at this moment this is just trial and error. So This value seems to be reasonable, 0.002, and I've set L2 penalty and using the liblinear solver. Linear underscore model ridge classifier, and here let's set the alpha to 0.5, that's halfway. Tolerance, I'll put the same tolerance as above. Solver is equal to auto, and let's add a name, the ridge classifier, and then the next one we have is linear underscore model dot perceptron, and for this penalty is equal to, in this case I'm adding elastic net, and max iterations, max iter is equal to 50, and then finally adding the name Perceptron for that model. And after this we'll use the passive aggressive, so model dot passive aggressive classifier, tolerance again 1 e to the power minus 2, max iter is equal to 50, and name this as passive aggressive classifier. Now again, all these models are definitely not the best models to be used with this particular type of data, but because this is an exercise I'm using all of them. Then we have linear discriminant analysis and solver. In this case I'm using the least square because I want to add the shrinkage of 0.5, and that works only with this solver. LDA as the name, and then we have the last one, quadratic discriminant analysis, and for this you can specify the regularization parameter as reg underscore param, and again this is QDA for quadratic. So those are the items that we need in that list, from which each iteration, sorry, this should be for each of this list it'll pick CLF would be this part, and then the name would be this part, and put a colon there. Now we'll first print the name, so print, I'll add some hashes there, and then print the name, and then the results dot append. So here what we are going to do is fit underscore predict, that's the function we created above, and to that we'll supply the classifier. So this particular part of the classifier will come in right here, and that will be used to fit and then predict to get us the metrics. And with that, the second part that we need is the name that needs to be saved. So all of this will go into the results and be saved. So let's run that. I'm missing a comma, and there's results is not defined, so that should be an S there. And there's another metric is not defined, accuracy matrix. Names is not defined, all right, because we call it name and not names. So okay, cool. So this is now working. So we have all these different types of classifiers, output of those, all of them seem to have an accuracy of 1. Maybe it's just for this data set, that's the case. Before ending this, I also wanted to run this for the SGD classifier. So let's try that. For penalty in, and here we use L2, L1, and then elastic net. Again, print hash is 25, print SGD classifier and penalty, so the type of penalty that is used, and then put a percent sign. So this is another way to write a print statement, penalty dot upper. Okay, and now we'll append this to the results. So results dot append, and within this we can specify two things. First is the classifier itself. So fit underscore predict, we are calling that linear underscore model dot SGD classifier, and it has alpha alias 0. Alpha 1 e to the power minus 2, and then max underscore iter is equal to 50, penalty is equal to penalty, and then specify the name SGD classifier. Before we run this, let's just check the SGD classifier. So it's linear underscore model SGD classifier, and here we can see, so that's the default value of alpha is 1 e to the power minus 3, and we are using 1 e to the power minus 2 instead. So okay, so let's run this now, and here why don't we add a space, so maybe like so. Okay, so those are all the, and here we can see that the SGD classifier has around 0.99, 0.98. Now if you look at the results, it has a confusion matrix in there. So these are all 1, 1, 1, and the LDA is 0.96, quadratic is 99. So this could be that this is overfitting. This is also 0.99, and this is the case after we remove the collinear feature. If we just want to check what would happen without removing those, so I'm commenting this out. Now run this, and then run all the cells all over again and see what results we get. Okay, so as you can see, the accuracy it's pretty still close to 1, although it went down a bit for logistic regression, but I still think this went down to 0.97, and yeah, so this may be overfitting. If we have a new data set that for the same mushrooms with the same number of features, same type of features, and if you try to run those as to get the predictions, I wouldn't be surprised if the accuracy drops much below what we see here. So that was it for this video. I hope you enjoyed this first project in this particular series. I'm working on some new projects as well. So the next, I think I'm trying to reach 5 projects before we move on back into sklearn. So if you have any comments or suggestions, please let me know in the comment section below. If there are any other things that you'd like to see added in this particular and session of working on a project. This was very first project. It was a still smaller data set, just around 8,000 records. But we'll slowly try to move into a much larger data set. And for that, um, we may have to use online resource such as Google Colab to train the model. So we'll see how that goes. Until then, please like, share, and subscribe. I hope to see you all in the next video. Thank you.